Hello, everybody. So, last time in valence bond theory, we introduced uh, the fact that if I'm trying to use a pz, a px, and a py orbital to describe my system, it's going to start to give inaccurate results if I'm using these to control the overlaps. So, instead, what we are going to do is building up a set of hybrid orbitals, which will give us a better description of our system. So the technique we're using is a technique we've actually used before. If I have a set of orbitals that poorly describes my system, I can go ahead and combine them together to give me a new set that fits my needs better. In fact, this was the exact method we used to get my py and px orbitals. Because remember, these are made from a linear combination of the m sub l plus and minus 1 orbitals. So there's nothing saying that these px, py, and pz p orbitals are the ones I have to use in valence bond theory. Any combination that I use from these orbitals, or more appropriately, from my original eigenfunctions, will work in a pinch. So let's build a new set of orbitals and see if they work any better. So we started with a set of 4 valence orbitals, 1s and 3 different p orbitals. And we can go ahead and try and use these to build up a set of 4 equivalent orthonormal orbitals. So these should still all have no overlap with each other, and when we integrate each one individually, it should give us a value of 1. So ideally, in order to generate orthonormality, each one of these orbitals should point in a different direction. That way, we'll minimize any overlap in the x, y, and z direction, because we've long since given up trying to ensure a lack of overlap by making use of momentum. So I'm going to introduce my single s orbital and my 3 p orbitals. And when I put them in a bag, I shake them out, I'm going to get 4 orbitals out. So 4 orbitals in, 4 orbitals out. And each one of these orbitals is going to be composed of 1 part s and 3 part p orbitals. And so what we can do is, by making sure that they're all orthogonal and pointing in different directions, this is going to give us a big advantage when I build up bonding, because this is going to ensure that all 4 of our bonds are going to be maximally separated. So whether I've got 4 bonds, 4 lone pairs, I've ensured maximum physical separation. Now, electrons can dodge around each other a little bit better, which is the reason we didn't build this up for atomic orbitals. But if I'm introducing a field of a net atom outside of each of these orbitals, in other words, if I'm building up a molecule, it turns out that I'm really going to need this hybridization to lower the energy of my entire compound. So this is the basic idea. Let's get into the mathematics. So we've got 3 p orbitals, 1 pointed in the x direction, 1 pointed in the y direction, and 1 pointed in the z direction. So ideally, I'm going to combine my x, y, and z to give me 4 different orbitals that will point in each of the diagonals. Unfortunately, you may notice I've got 3 directional orbitals. I want 4 directional orbitals when I'm all done. So we bring in the s to essentially give us that extra orbital, and it's going to give us some energy lowering features as well. So ideally, I'm going to start to try and make this first orbital that points up in the x, y, and z directions. And being an sp3 orbital, it's going to have equal parts of my 4 orbitals. So when I do this, I'm going to have a 1/4 character of s, 1/4 of px, 1/4 of py, and 1/4 of pz. And because the way C's work, we take the square root of the probability or ratio of each of these species. In truth, there will be an additional normalization constant out here, but we're going to ignore that right now for simple convenience. So this first orbital is going to have some rounded character from the s, which is the furthest out of my four orbitals, but it's also the lowest energy. So this one gives me no direction, but lowers my energy and controls a little bit of how far out my bond is. And then I build in each of these to give me direction. They'll all collectively point up. And so that's the direction of my resulting axis, with again, this s orbital uh, will slightly lower the energy with respect to my p orbitals. Because again, s generally have lower energy than p orbitals because of that electron penetration. Now we run into a slight issue here because I combined four orbitals and I got one orbital out. Well, that means I've got 3/4 character of each of these remaining orbitals that I have to combine, and I have to get four orbitals out. Four orbitals in, four orbitals out. So the trick is then going to be generating one orbital that goes up and back, and then two orbitals that go down and to the side. And we can do this mathematically to generate my four hybrid orbitals. So our first one goes all up. Our second one goes up and back. So back in the y direction, back in the x direction. That's really what these negative signs are telling me. And then my next two sets of orbitals will both go down. And since I want them to go to the side, one will go forward in the x direction, but back in the y, and the other one the exact reverse, giving them mirror images of each other. And when we combine these four together, they'll be maximally separated. And it turns out that the maximum separation is going to have each of these orbitals pointing 109.5 degrees away from each other. And this is the best we can actually do to get four things pointed as far as possible. So here's our winning combination. And the nice thing is that this actually lines up with such molecules as methane, where this is indeed the angle we have. So we've generated a real set of orbitals that does correspond to the geometries we see experimentally. So that means that it must be possible to use these new atomic orbitals and use them to build atoms. So we're going to continue using our valence bond theory, which means I now have four orbitals. And if they are going to be singly occupied, any bonds will be generated by the overlap of one orbital out here and any singly occupied orbital. But that's the trick. I need to figure out which one of these hybrid orbitals will be occupied and which won't. And this becomes incredibly important as when we started with our original set of orbitals, all four orbitals had a slightly different energy. Well, the s orbital had a slightly different energy and the p's were less stable. However, when I took all of these orbitals and I shook them up, I made every single one of them equivalent, which means that they're going to be slightly lower in energy than my p orbitals, but slightly higher in energy than my s. Now, the character is where in the middle are they? Well, the answer comes from how much of each character they have. So they've got 1/4 of the s character and 3/4 of p character, which means that's exactly where the energy ends up lining up. So you can get the energy of my hybrid orbital by taking the energy of your s orbital and the energy of your p orbitals and combining them in a 3-to-1 ratio. Now, what's really important about this is because the energies of each of these orbitals changed, so will the occupation. So a great example of this case is looking at elemental carbon. So if I have elemental carbon, this means I naturally have 4 electrons. So using Hund's rules, I'm going to put 2 of them in the s orbital and 2 of them in the p orbitals. And Hund's says that they'll go ahead and separate out. Classic Aufbau. Now, here's the trick. This orbital went up in energy, these 3 went down. Now that means that there is nothing favoring one of these orbitals with respect to the other. So if I've got four orbitals and I've got four electrons, as long as those orbitals are the same energy, those electrons are going to follow Hans and spread out and all point in the same direction. So this means that for carbon, we've got four equivalent electrons. And this drives a lot of carbon reactivity. Now, because carbon's a little bit messy, we're going to walk back to our example from last lecture. Let's look at water. So again, water, its major focus is going to be that central atom of oxygen with its 6 electrons. This means I'm going to have 2 occupied hybrid orbitals, fully occupied, and 2 partially occupied. Well, those 2 partially occupied hybrid orbitals are going to have an overlap with my hydrogen 1s orbital. And the net bond is going to be something that we've seen before. I'm going to have my normalization constant, and then I'm going to have some hybrid carrier, 1 electron on the hybrid orbital, 1 electron on the hydrogen. But because of indistinguishability, I'm also going to have the combination of the reverse. And again, because I'm maximizing overlap, I've got the symmetric combination, meaning that my electrons have to be asymmetric or paired. So 1 electron up, 1 electron down, nice singlet system with an overlap. This is the bread and butter of valence theory. So if I've got two hydrogen atoms and 2 partially occupied orbitals, I'll have 1 hydrogen here, 1 hydrogen down here. And this overlap will generate a bond, or again, a constructive wave function. So maximum probability density is going to be here. Bring these 2 atoms close together. We love bonds. But the problem is that when I'm dealing with water, this gives me two sets of orbitals that only have electrons and no atom at the end. Well, we can still treat this the way we've always done. So what we can have is our additional lone pair is going to put 1 electron on the hybrid orbital, 2nd electron on the hybrid orbital, and that's where they are. Both electrons are going to be on this same hybrid orbital, and because they're in the same location, we have to again pair the spins. And again, each of these orbitals will be doubly occupied. I'll have 2 sigma orbitals, each with 2 electrons, and 2 lone pair orbitals, each with 2 electrons. So putting this together, what we have again seen is, like we had before, you can construct lone pairs using valence bond theory, whether it's on a p orbital or a hybrid orbital. Similarly, you can use these hybrid orbitals to make bond overlaps, just like we did with s orbitals and just like we did with p orbitals. Not much actually functionally changes. And so our bread and butter of organic chemistry, sp3, is a fairly easy system to treat, though it looks a little bit weird when we're trying to figure out where they came from the atomic orbital perspective, because each one of these hybrid orbitals is composed of 4 separate orbitals, or depending on how you write it, you can actually break it down to as little as 2. But more or less, in each of these hybrid orbitals, it contains a multitude of atomic orbitals. But superpositions are nothing weird for the good quantum chemist. But we do run into a slight problem. If I'm using sp3 hybridization, all I'm going to get is tetrahedral structures. You can't use this if there's a double bond present. So we need to find a way around that. Well, the argument for double bonds is actually fairly simple, because when I have a double bond, all 4 orbitals aren't equivalent. One of these sets of orbitals, one of my p orbitals, is going to become fixed, and it's going to become fixed in a double bond. Because again, a double bond requires a p orbital, and that p orbital won't be allowed to move unless I break the double bond. So I lose 1 p orbital. So I'm going to hybridize every one I have left, because this will help drive my energies lower. And when I do this, what we're going to end up forming is a set of 3 hybrid sp2 orbitals, because I'm down to a single s orbital and 2 p orbitals. So When I do this, I'm going to have 3 hybrid orbitals, and I'm going to use a slightly different form here to help simplify things. Because the simplest form I can have is, since I've got 3 sp2 orbitals, and each of these sp2 orbitals is going to have 1/3 s character and 2/3 p character, I'm going to build this in a slightly different form, where I'm literally going to take 1/3 of my s orbital and 2/3 of one of my p orbitals. You can choose px, py, or pz. In this case, I chose to use py. So again, when we add this together, 1/3 s, 2/3 y, I end up with a entire wave function. And this will end up generating a p orbital, which is slightly elongated out, has a little bit of penetration from the s, and becomes just, again, a little bit broader, all coming from this s character, and also slightly lower in energy. So this means I used up 1/3 of my s orbital and 2/3 of my py. And let's say I have my pz forming the double bond. Again, slightly different notation. You can feel free to be a little flexible. This means I've got 2 more orbitals I have to construct. Well, because it's an sp2 character, each one of these orbitals has to have 1/3 s character. So what am I going to do with the remaining character? So a good way to look at it is I now have one orbital just pointed in the y direction. So this means that I'm going to have 2 more orbitals who are going to point in the negative y direction. They're going to point a little bit back, but they're also going to point to the side. So I can start with one that points back with a 1/6 character, so half of my remaining y character, and then half of my remaining x character will point it this way, because I've got 2 more orbitals to make. So I'm going to literally take 1/2 of each of my remaining 3 orbitals. So half of my remaining s is 1/3, half of my remaining x is 1/3, and half of my remaining y is 1/6. So this will help point the orbital back and to the side. And I'll generate another hybrid orbital that points in this direction. So it's going to be equivalent, just rotated 120 degrees. And then we can do this again. Now it's pointed back in the y and back in the x direction, again, rotating another 120 degrees. So I'll have 3 hybrid orbitals, all pointed 120 degrees away from each other, which, with the remaining p orbital occupying all of the z direction, is going to be the best way to get all 3 of these bonds maximally separated from each other. So you've probably seen these orbitals before. Now we're just kind of giving a mathematical construction of them. And just like we used our sp3 orbitals to build molecules, we can do the same thing with sp2. So let's choose one of the simplest molecules that contains a double bond. Who doesn't love ethylene or ethene? So this case, I've got 2 carbons, a double bond, and hydrogens everywhere else. So we can depict our double bond as the overlap of 2 different sets of orbitals. So the first is going to be my hybrid sp2 orbitals. I'm going to take 2 of them, one on the first carbon, one on the second, combine them in a symmetric fashion, because this is going to give me the best overlap and the lowest energy bond. And because these are symmetric, I have a paired spin. I have another nice sigma bond. So just like we did before, hybrid orbitals are great at making sigma bonds and lone pairs. In this case, we're all out of lone pairs, so into a carbon-carbon sigma bond. So our remaining 2 hybrid orbitals can make a similar overlap with our 4 hydrogens sitting out on the ends of the molecule. So when we pair this together, we'll end up with 5 sigma bonds, 2 from overlapping hybrids, and then 2 with overlapping 1s hydrogens. And we've already seen that form before, so I won't repeat that. But that leaves us a remaining set of hybrid bonds, or pi bonds. So these are just going to be our remaining pz orbitals. So we've seen this guy before when dealing with nitrogen. Now I've got 1 electron on carbon 1, 1 electron on carbon 2. Have to worry about identical the identical nature of an electron. So we've got the exchange part, and then because I have symmetric combinations of my orbital portion, my electrons have to be paired. Throw in a normalization function for convenience, and there we go. We now have a new pi bond. So again, all of these bonds will be doubly occupied, 2 electrons per. So I'll have 4 carbon-hydrogen bonds, 1 carbon-carbon, 1 carbon-carbon double bond. All of them are doubly occupied, as denoted by this 1,2 notation. So putting this all together, congratulations, we've now made ethene from, valence bond theory. So all that leaves us left with is trying to figure out how to make a triple bond. So for this, we're going to need to fix another p orbital in order to make a double bond in the opposite direction. All this is going to leave me behind with is a single s orbital and a single p orbital. At least that makes the linear combinations fairly easy. Each orbital is going to have to be 50% s and 50% p. That's it. And to prevent the 2 orbitals from being identical, one is going to be an additive combination and one will be a negative. So one way to look at this is I'm going to take my s orbital, and again, this should be much bigger. It should even be bigger round than the p orbital. I'm going to mix this with my p orbital, and I'll have one that points in the positive z direction, one that points in the negative z direction, and when we combine it, we had constructive interference along the z in between the 2 orbitals and destructive in the remaining directions. So congratulations, we've now generated our full set of sp orbitals. Oh, how hard it was. But it is important to note what each orbital brings to the table. And I'm going to repeat this yet again. So the p orbital is really giving us our direction. What the s orbital is giving is it's rounding it out, making it a little bit further out along the axes, but more importantly, also spreading it out in the x and the y directions. So making the function more rounded, because that's what s orbitals do. In addition, it's going to give this orbital a little bit extra penetration, which is going to help lower the energy. And again, these sp orbitals will be much lower in energy than sp2 or sp3 because they didn't have to bring in that extra p character with them. So with now a full set of sp orbitals, we can end up building a nice triple bond species. Let's keep it simple. Let's go to ethine. So C2H2, about as simple as it gets. So in this case, I've got my bond will be made of 3 different pairs of electrons in 3 different sets of overlapping orbitals. So again, the simplest set is going to be this sigma bond from overlapping hybrid orbitals, one centered on the first carbon, one centered on the second. And again, with having to deal with electron exchange, one electron will be on carbon 1, second electron will be on carbon 2, and switch, with again, this forcing the electrons to be paired up with opposite spins. Then we can also build up my first set of pi orbitals by having my 2 px orbitals ending up overlapping. Again, different electrons on different carbons, then switch, 50% combination of each, and the spins have to be paired. So up electron, down electron, and then flipped with an anti-symmetric combination. That's again really generating our paired spins. And then we'll do the same thing in our remaining y direction. So we put this together, we've got 3 bonding orbitals with our remaining extra electron on each carbon going to a sigma bond with the hydrogen. So again, this will look very similar to our previous sigma bonds between any second row element and a hydrogen atom. So this gives us our simple approach to how we can use valence bond theory to describe fairly large atoms. So if we had a lot more time, you can even extend this to bringing in d orbitals and d orbital hybridization if you need to, though usually d orbitals will stand out and not hybridize in due to their relatively higher energy and less reactivity. Uh, but this ends up bringing us to the end of valence bond theory. Next time, we're going to be taking a bit of a step forward and a bit of a step back as we return to the hydrogen molecule. And we're going to be doing this as we're going to have to build up a set of Hamiltonians that we can use to start treating our brand new wave functions. All right, see you then. Take care. Stay healthy.